Assalamu alaikum everyone. So lecture number 27, and we will be switching to an important topic, that is counters, right? So these are the main points which we will be discussing in today's lecture, right? As counters are very important component within the computer or computer system, right? So you can increment or decrement, right, according to your desire, right? And we can construct counters by using different flip-flops. You can have T flip-flops, and you can also use JK flip-flops and T flip-flops, right? So then we have different types of counters, right? Ripple counters, right? And then we have Johnson counter, we have up-down counters, right? So there are different types of counters which we will be discussing, right? And we can also have synchronous counters, right? So we will see what a synchronous counter looks like, right? So and how we differentiate between synchronous and asynchronous counters, right? So these are the main points. So let's start. So actually a counter is a register that go through or that went under prescribed number of states, right? So for example, I need a 3-bit counter, right? So I want that it should start from 000, right, and until 111, right? So then I need 3 registers, right, 3 flip-flops, right, and I will join or cascade those flip-flops accordingly, right? So after the cascading, right, so now the next important step is how I will move or shift those ones, right, and how I will reset. So these are the important points that I have to take into account, right? So if I want to define a counter, so a counter is a register that go through a predefined or prescribed number of states, right, or series of states, right? So we can have a binary counter, right, and we can also have a ripple counter, right? And there are some of applications that is mentioned over here regarding the counters. We can use those counters in our watches, right? Digital watches, clocks, they can also be used, right, for clocks. Then alarms, right? So you want to alarm after a certain state, so you can also use a counter. Then you have seen that sometime a web page, it refreshes itself after a predefined amount of time, right? So you set a counter, right, a counting time, and the time decrements, and after it approaches 0, your web page refreshes itself automatically, right? So these are few of the applications of counters, right? So actually it is a register, but you can see a group of register where you cascade those registers or connect those registers in such a way that it counts, right, and it go through or it undergo certain series of states, right? This is again the same definition, right? So so here you can see that we have asynchronous ripple counter, right? Then synchronous counter, and we can also have a decade counter, right? So decade mean that counts through tens state per stage, right? And we can also have up-down counter, right? We can construct a counter that can count up, right, starting from 000, and that can also count down starting from 111. If we have, for example, 3 bits, so we can start count down from 111 till 0 in the reverse order, right? And then we can have the ring counter, right? So whenever we will reach the maximum count, it will move back or reset to the or start counting from 0 0, right? Then we have a Johnson counter, right, and cascaded counter, right? So let's start the design procedure for a counter, right? So here we have the example, right? So you can see we have the present state. We have 3 bits, right? C, B, and A. These are the next states, and these are the flip-flops, right? So if you look here, we have started from 0 0 0, and then 0 0 1, 0 1 0, and 0 1 1, right? 1 0 0, 1 0 1, 1 1 0, and 1 1. And after that, you can see that we have moved to the 0 0 state, right? So everything has been reset, and we have started counting again, right? So this is the maximum count that this counter can do, right? So here 0 0 0, so obviously next state is 0 0 1, so this has to move here, right? So 0 0 1, and then we have the next state 0 1 0, this next state will go here, and then we have the next state, right? So this will go like this, right? So here if you see, this 101 moved here, 101, and the next state is 110, right? And this is also important. After 111, you can see that all the columns have been reset to zeros, right? So, and these are the input for the flip-flops that has been used, or that has to be used, right? So this is TC, TB, and TA, right? And this is plus is mentioning the next state, right? So this is a sort of state table mentioning all these states, and this is the state diagram, right? We know very well those different entities, right? And then in the next state, what we need to do, we have to simplify, right? So the process is the same, right? So here we have the K map, right, for those different, right? So here if so this is for TA, right, and this is for TB, right, and finally we have for TC, right? So here you can see we have TC 2 ones, for TB we have 3 ones, and for TA we have all ones, right? Right. So for TA, right, so TA we have all ones, so we have the quad, right? So after the mapping, after the plotting of those values, we have the quad, right? So we have the 1, right? So it means that this flip-flop need or require 1 all the time, right? Right. So here we have TB, that is for this we have this quad 4 ones, right? And for TC we have this pair. So as a result of this pair we have A dot B, right? So now what we need to do, we need to plot, right? So you can see for this is C, right? So for TC we have AB, so this is B and this is A, right? For TB we have A, so this A has to be inserted into B, right? For TA, right, so we have 1 all the time, right? So this is, you can see this is mentioning 1 all the time, right? So we have to provide, so this is the reset. If we want to reset the counter at any point in time, so we have to make a reset, right? And this is the clock, right? So you can see at the bubble, so this is active low, so this is the clock, and this is also the count, right? And here we have the timing diagram, and this is also very important, right? So here we have the count, right? So we have we will be counting, right, the number of pulses, right? Okay, right. So next we will be moving to binary ripple counter, right? So first you can see the reset, right? So this reset is connected to all the reset inputs of the flip-flops, right? So we have a 4-bit register over here, and they are connected in this way, right? And then whenever we want to start counting, right, so count signal toggles output of low order flip-flop, right? So here when we want to start counting, right, so the lower order, right, so if I start from A3, A2, A1, and this is the lowest order A0, right, so this flip-flop has to be toggle, right, because we are using T flip-flops, right? And as a result, this will trigger this, right, and this will be toggled, right, and in the next clock we will be having a clock input. So there is some difference, right? So here you can see that the output of this lower order flip-flop is provided as a clock to the next flip-flop, right? So here output of A1 is the clock of A2, output of A2 is clock for A3, right? So it means all the flip-flops, they will not be changing their states simultaneously, right? So in the first clock we will be having toggle here, right? So that toggle will affect this, right, because this is the clock. So now the clock has been provided, right? So then this will toggle, and this will toggle will be applied as an input to this clock, right? So there will be a ripple effect, right? So the clock will be moving step by step, right, like the ripple effect. So that's why we named it a binary ripple counter, right? So this is the asynchronous ripple counter, right? So here we have used T flip-flops, right, and here we have used JK flip-flops, right? So here if you want to know that the medium scale integration counters, integrated counters, right, they normally are of two types, right, ripple counters and synchronous counters, right? So we have discussed the ripple counters, right? So that is over here we have used T flip-flops, right? So now we are going to discuss the ripple counters, right, but here we have used JK flip-flop, right? So here you can see this is the clock, and this is the output of this flip-flop, and that has been provided as the input, right, over this clock signal, right? And we can think about this bubble. So it means this is active low, right? So falling edge, right? So it will, JK flip-flop will trigger on the falling edge, right? So here we have the clock, right? So if I talk about the timing diagram, right, so this is A, right, and this is B, and this is C, and this is D, right? So here if I have ones, so I assume that this JK and this JK and this, all the flip-flops have ones all the time, right? So here we have A, that is the output of this JK flip-flop, and that is actually the clock for the next flip-flop, right? So for A, what will happen, right? So JK all time 1, right? So we can see that there is a toggle, right? So we will have a 1, right? So if you know the truth table, so JK11, so it has to toggle, right? Again, it will remain in this state till the next active clock edge arrives. So again we have a toggle here from 0 to 1, and here we have a toggle again, right? So this will continue like this, right? Toggle, right? Toggle, and we will be switching between zeros and ones, right? So this, remember, this A is the input, or this A is the input for this clock, right? So you can say that this is the clock for the B flip-flop, right? So now we have the clock, right? So this is the clock, right? So this is the clock, right? So let me mark the falling edge, falling edge, falling edge, and falling edge. Here again falling edge, falling edge, right? So now I will be doing the same. This is my clock, right? And I have assumed that all the JKs are ones all the time, right? So now I will be computing the output for this flip-flop, right? So that is very important and key point, right? So this is the output, right, for this flip-flop, mentioned or named A. Now you can see that this output is the clock for the next flip-flop. So I have declared that this is the clock, right? This is my clock now, right? So before I have taken this as clock, now this is my clock, right? So JK11, right? So if I start from 0, I assume that this is 0, then it has to be toggle on the active or falling edge, right? So it will remain till the next active or falling edge arrives, right? So here we have toggle, right? So 1, and this one will remain 1 till the next falling edge arrives. So now again we have to toggle, because again I have to mention that JK are ones all the time, right? So here again 1, 0, right? So it will remain 0 till the next clock edge arrives. So right, so here again toggle, 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 and now this is the output B, right? And here you can see that this output is clock for the next JK flip-flop, right? So let me write down or mention, right? So here again falling edge, falling edge, and falling edge, falling edge, right? So now this is my clock, and I have 1 1 all the time at this JK flip-flop, right? So I have assumed all the flip-flops are reset to 0 regarding the output, right? So 0 on the falling edge, it has to toggle, right? Again it will remain 1 till the next falling edge, right? So now toggle from 1 to 0, and this will remain 0, right, till the next active clock edge arrives or the falling edge arrives. So again toggle from 0 to 1, and this will continue like this, right? So now this is the clock for D, right? So here we can see this is the falling edge, right? So let me mention falling edge and falling edge, right? So here you can see that what we have D, right? All JKs are 1 all the time, so it will toggle on the active clock edge, falling edge, right? So it will remain 1 till we have the next active clock, that is the falling edge, right? And it will remain 0, right? So if I write down those values, right? So 0 0 0, you can see A B C D. So 0 0 1, right? So you can see 0 0 0 and 1, right? And then 0 0 1 0, right? So let me write down the values, right? So here we have 0 0 0 0, right? So here we have 0 0 and this is 1, you can see, right? And here we have 0 0 1 0, right? And here we have 0 0, right? 1 1, right? Again 0 1 0 0, right? And here again 0 1 0 1, right? 0 1 1 0, right? And here we have 0 1 1 1, all ones, right? So here we have this 1 0 0 0, right? So 1 0 0 1, right? And here we have 1 0 1 0, right? 1 0 1 1, right? 1 1 0 0, right? So 1 1 0 1, right? 1 1 1 0, right? So here we have 1 1 1 1, right? And here we have a reset, right? On the next clock we have 0 0, right? And next here we have 0 0 0 1, right? So after that the counter will start counting again, right? So this is the same example, but here what is different, that we have used the JK flip-flop, right? So here again you can see that this is the same sort of situation, right? So here this is this output is the clock for the next flip-flop, and this output is the clock for the next flip-flop, right? Okay, and now we will be having the table, right? So here we have A3, A2, A1, A0, right? So you can see that this is almost the same, right? So we have the table, right? Okay, then we can also have the decade decimal BCD counter, right? So this is a decade counter, right? It can count from 0 to 9, right? So you can see we have the 4 bit counter, right? So BCD, binary BCD counter, right? So here we have Q1, Q2, Q4 and Q8, right? So you can see the numbers, right? So this is 0, 2s, 4s and 8s, right? So let me write down. So this is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So 1, 2s and this 4s and 8s, right? So that's why we have 1, 2, 4, 8 in the subscript, right? So this is the another BCD counter, right? So you can see the interconnection, right? So these are the count pulses, right? So first whenever we have start counting, right? So you can see whenever we have 1 0 0 1, right? So that will trigger this, and then this will start counting, and then here we have, right? So you can have a counter like this, right? So if we have a 1 BCD counter, right, it can count from 0 to 9, as you can see that we can have counting, right? So zeros started from 0 0 0, and then we can have 1 0 0 1, that is 9, right? And then if you want to calculate or to count from 0 to 99, then we need 2 counters, 2 decade counters, right? So it means if you want to calculate or to count from 0 to 99, we need, right, So this is for 9, 0 to 9, this is again for 0 to 9, right? So this is units and tens, right? And if you want to count from 0 to 999, right? Units, tens, and this is hundreds, then we need this sort of configuration, right? So you can see the cascading. So here Q8 is connected as a count pulse for the next BCD counter, and this Q8 is connected as a count pulse to the next, right? So we now, by using this BCD counter, we can count from starting from 000 till 999, right? Okay, so after asynchronous counters, right? So you have realized that in asynchronous, right, the clock is not, or the global clock is not supplied to all the flip-flops, right? So actually the output of this flip-flop is acting as a clock for the next flip-flop, right? So this is a sort of asynchronous behavior, right? So clock is not synchronous for all the flip-flops, right? So here we have the synchronous counter, right? So the key difference over here, that we have the same clock, right? So you can see that the same clock signal is applied to all the flip-flops, right? So here you can see that we can have the count enable, right? So this is another control signal. If you want to start counting, you have to make this enable, right? And this is the clock, right? And over here you can also see the combination circuitry, right? So here you can see count enable, and this is the output, right? So A0, right? Output of this least significant bit flip-flop, right? So and then we have this is the input for J and K, right? And then we have right? So this is the difference, right? And we normally call those asynchronous counters, right, as parallel counters, right? So all the flip-flops, they are triggered simultaneously, right? So whenever we have the clock, so depending upon the input, all the flip-flops has to trigger, right? And so as a result, they will change their states at the same time, right? So here this is also the key point, right? Whenever we have JK00, right, this is from the truth table, no change, and when JK is equal to 1, we know that the JK flip-flop toggles, right? So usually in computers we use synchronous counters, right? We can also make those flip-flop, those counters by using the flip-flops, and we will be having them after a couple of slides, right? So here we have synchronous counter, right? So here you can see the same clock pulse, right, for all the flip-flops, right, mentioning the synchronous operation, right? And here you can see that we have the combinational circuitry, right? So AND gates. So this is A, this is B, and this is the input JK, right? So here this is the same, right? So except that here we have replaced this enable, count enable, by JK11 all the time, right? So now we have JK at this flip-flop position 11 all the time, right? So whenever we have the clock, right, so it will toggle, and we have right, the output, right, and then this will also toggle, right? So let's talk about the operation, right? So count 0, whenever we have count 0, 0, 0, 1, 001, right? So 10. So you can see that this is this sort of same operation, right? 0010, right? So we can have an idea, right? So here 0010, right? So after this state, right, it will reset, right? So after we have all 111, right? Here we have 1, here we have 1, and here. So let's verify this, right? So we have all ones, 1, 1, and as a result of this 1, 1, we have all ones, right? So in the next clock pulse, all has to, right, reset, right? So here we have 1 here, right? So this is, we have 1 here, right? As a result of this one, we will be having 1 here, 1 here, right? So this is what? This is 1. This is also 1, right? And C, this is also 1, right? And we have 1. So we have all. So this is also 1, right? So 1 1, right? So on the next clock pulse, right, 1 1, this will toggle to 0. 1 1, this will toggle to 0, and 1 1, this will toggle to 0, and this 1 1, this is toggle to 0, right? So this is the sort of verification that whenever we have this state 1 1 1 1 at all the flip-flops output, on the arrival of next active clock pulse, all the flip-flops will go to 0 state, right? Okay, and here we have the synchronous up down counter, right? So we have an extra provision over here, or control over here, right? We can count up as well as we can count down, right? So we have used T flip-flops, right? So here we have an extra control, that is up and down, right? So you can have up counter as well as we can have the down counter, right? So for the up counter, we, for example, we can think about the starting from 0 0 0, right? And we can count till 1 1 1 1. All flip-flops are 1 1, right? And then back to 0 0 0, right? And on the other hand, if you want to count down, right, so then we have to we can think about 1 1 1, and we can count down till we reach 0 0 0, and then we will go back to 1 1 1, right? So we can perform one operation at a time, right? So we can count up or we can count down, right? So we will be verifying this, right? So let's talk about count up, right? So I will be assuming that we have 1 here, 1 here, 0 here, and 0 here, right? And I have count up. So it means we have count up 1, down 0, right? So this 1 and this one will be 0, right? And as a result of this 0, we will be having 0, and we will be having a 1 here, right? Okay, and if you look here, right, so this 0 will be propagated here. I will be having a 0 here as a result of this 0, right? And this 1, right? So this is also 1, so I will be having a 1 here. So as a result, I will be having 1 here, right? Because any 1 will make the R output 1, right? So this 1 will propagate here. This is 1, so again 1, and we will be having a 1 here, right? And this is 0, right? This is 0, right? This is 1, we have a 0 here, right? And here that will be what? 0, right? And 0 and 0, right? So whenever we talk about T flip-flop, right, so no change, it will toggle, right? So 0, this is the next state I'm writing down, right? 1, so I'm writing like this, right, in this direction, right? So this is 0 and this is 0, right? So you can see that if this is the most significant bit and this is the least significant bit, right? So before what we have 3, and on the next clock that 3 will be 4, right? Now we have the 4, 0, 1, 0, 0. So this is when we have the count up high and count down at 0, right? So let's move to the, now we can have another scenario. Countdown is 0 and countdown is 1 and count up is 0, right? So this will be 1, right? And this is already 1, so we will be having a 1 here, right? As a result of this one, we will be having 1, right? Okay, and this one will propagate here, right? So we will be having a 1, right? So I'm assuming the same state, right? 1, 1, 0, 0, right? So this one will propagate here, and here we have a 0, right? So as a result of this, we will be having a 0 here, right? 0, 0, so this is 0, right? So here we have 1, right? And this is what? 0. We will be having 0 here, right? This 0 will propagate here, and I will be having a 0 here, right? So this 0 will propagate here, right? 0, and I will be having 0, right? And for this 0, this 0 will propagate here, and 0 and 0, I will be having a 0 here, right? So you can see that only this flip-flop will be toggled, right? So it means we will be having a 0 here, right? So 0, no change, right? 0, no change, right? 0, no change, right? So 0, 0, 1, 0, right? So before we have 3 and now we have 2, right? So because this is 2, if this is the most significant bit and this is the least significant bit, so now you can see that we have the 2, right? So here you can see that when we have count down 1, count up 0, so the flip-flops or the register has been decremented, right? So this is the functionality of the synchronous up-down counter, right? And here we have added another control, that is the parallel load, right? So you can see that we have a control named count, right? And then we have another control, that is the load, right? So this control has been introduced due to the reason that we want to load the data, right, onto the counter or onto the registers, or we want to store predefined data into those registers or into those flip-flops, right? So if we have for example some data, right? So let's talk about 1 0 0 1, and you want to load that data into those flip-flops before you start counting, right? So 1, right? So that 1, and now we have to make the load high, right? So it means 1, this is double complement, so we will be having 1, so 1 1 1, any 1, so irrespective of the second input we will be having the 1, right? So again here we have 1, yes, so here we have 0, so as a result of this 0 we will be having a 0 here, right, and 0 here, so I have to look for, right, so this will be what, right? So this is count is 0. Now we don't want to count, we only want to load the data, right? So we are having a 0 as a result of this 0, this is 0, right? So this is from A0, right? So we also have to take into account the current value, right, of the flip-flop, right? So for example, if you have, right, so here we can calculate this, right? So this is 0, right? So we will be having a 0, right? So this is what, this is again 0, right? So we will be having 0. So it means we have 1 0, right? So 1 0, it means Q or output will be following J, so it means 1, right? So we will be having a 1 here, right? So that one will be here, right? So as a result of this we have a 0 and 0, right? So this is 0 1, right, 1, so we have a 1 1, right? So it means Q follows J, so 0 will be stored, right? So you can have an idea from those 2 bits that they are being loaded, right? So after the loading of the data, what we can do, we can start the counting. If you want to start counting from a predefined number, right? So this is the advantage of that counter, that we can load the data in a parallel fashion, right? So here you can have different possibilities, because we have clear, and we have also the clock, and we have also the load and the count, right? So whenever we have clock, no clock, right, if clear is 0, so it means we have to clear the counter, right? So all the flip-flops will be reset to 0, right? So whenever clear is 1, because this is active low, right? So on 0 we will be clearing the flip-flop or resetting the flip-flop to zeros, right? So this is the clock, right? And here you can see we have load, and whatever the value of X is, right, count is, we will be loading the inputs, right? And on the other side, if we have load 0 and count 1, right, so here we will be counting, right? So whenever we are loading the data, whatever the count is, we will be actually loading the data. These are the values which we will be loading, right? And then if we have load 0, count 1, we will be counting, and both zeros, it means no change, right? So they will retain their previous state, right? So this is the possible, these are the possibilities, different possibilities, right? Or you can say the function table for this circuitry, right? Okay, so here we have the binary counter with parallel load and preset, right? So you can see that we have JK flip-flops, right? So these are the JKs, they are 1 all the time, right? And here we have a clock, single clock for all the flip-flops, right? And you can see the combinational circuitry, right? So we have the parallel data P0, P1 and P2, right? That can be loaded, right? So here we have the parallel load, right? So this is complement, right, is indicating that this is active low. Whenever we have PL is equal to 0, we will be loading P's into the flip-flops, right? So if we have load 0, so it means we have 1 here. So let's do this, right? So we want to load 1 0 1, right? And load PL is 0, so that 0 will make this 1, right? So this is active low, so that one will be here, right? So we want to make this P2 so is 1, so it means this is 0, right? So it means 1 1 0, right? So it means okay, and now here we have 0, so it means this is 1, right? So this is 1, right? So here we have 0, right? And here we have 1, right? So that one is actually 0, right? So as a result of this 0, we will be having 1 at the output of this NAND gate, right? So it means here we have a clear, right? So here we have so 1, and this is coming from where? This is coming from, right? So I will be having a 0, right? No preset, right? So here we have a 0. As a result of this 0, I will be having 1, so it means preset, right? So here 1, right? And what is this? This is 1 0, right? So you can see that as a result of this, right? So I have to start from here, right? So it means we will be having the data, so all JK all the time 1 1, right? So we will be having a 1 here, right? And a 0 here, right? And a 1 here, right? That data has been loaded now, right? And then we can also have after the loading, if we want to start the counting, we can start the counting, right? So this is almost a similar example, right? So but here we have the more control after the introduction of preset, right, and clear. So this is the IC, integrated circuitry, and its data sheet, right? So you can see that we have different pin configuration, right, and their description, right? Okay, so till now we have only utilized JK and T flip-flops in order to design counters, right? So now we are moving or switching towards the counters by using D flip-flops, right? So here you can see that we have a counter, right? And but we have used here D flip-flops, right? And you can also see the XOR gates, right? So here if you want to, in order to start the counting, we have to enable, right? So it means this has to be 1, and this is the clock, right? So it means we have the global or single clock for all the flip-flops, right? So if you talk about the Boolean expression, so these are the Boolean expressions for those different values. Q0 we have for D0 we have Q0 XORed with enable. For D1 we have Q1 XORed with Q0. You can see for this is for D1, and this is Q1 XORed with Q0 and enable, right? So Q0 dot enable, right? So and so forth, right? And we can also have the counter with parallel load, right? But remember that here we are using parallel D flip-flops, right? So what is different from here, this different over this slide. So if you compare, here we have the XOR gate, and here we have the XOR gate and a multiplexer, right? So 2 into 1 multiplexers, so you can see the 2 into 1 mux, right? So it means we can have right, enable for counting, right? And we can have those D's in order to load the data, right? So whenever we want to load the data, right, so we have to provide those D's, right? So enable should be low, right? So during that time span when we are actually loading data, right? And so we can have a control, right? So this is the carry out, right? So this is the counter, 4-bit binary counter with D flip-flop, and this is the same counter, but over here we can load predefined set of data, right? For example, if you want to load the value, right, 1 0 0 1, so what we need to do, we need to make this enable low, and this will be, right, selected, 1 will be selected, and as a result the data will be loaded, right? Because Q follows D, right? As we all know in case of D latch, D flip-flop, right? Okay, so this is almost the same, and here we have the BCD counter, right? So you can see that we have D's and Q's, right? So this is the enable, and this is the data, right? So starting from D0, D1, and these are the Q's representing the output, right? So you can see that this is the BCD 0, right? So you can see it can count from 0 to 9, right? And it can count from 0 to 9. So overall we can count from 0 to 99, because this will be from for 9, right? So this is for, you can say, units, this is for units, and this is for tens, right? So this is another configuration for BCD counter, right? Okay, so here we have the ring counter, but the difference is that here we have utilized D flip-flop, right? So the ring counter, what normally happen, right? So you can see that this is the most significant bit, right? And this is the least significant bit, right? So and this is the feedback, right? So you can see that this is the feedback loop, right, over here. So similarly we have represented this feedback loop, right? So this is the clock, QA, QB, QC, and QD, right? So you can see that after this counter reach, right, a certain state, then it will be reset, right? So it will be, so starts from 1 0 0 0, right, 1 3 0 0 1 0 0, right, and so forth, and after that it will be repeating, right? So it's a sort of ring, right? So you can see that we have a ring sort of, right? So here we have another counter, right, and utilize the D flip-flops, right? So this is something different, right? So we have a Johnson counter over here, right? And you can see that we have flip-flops, right? So the only difference is that you can see the feedback loop, right? But right, so if I go back, right, so here we have the feedback loop from Q, right? So over here we have the feedback loop from Q bar, right? So this is something different, and we normally call it a twisted ring counter, right? Inverted output of the last flip-flop is connected to the input of the first flip-flop, right? So it will start counting from 0 0 0, right, 1 0 0, 1 1 0, 1 1, right, and then 0 1 1 and 0 0 1, and sequence is repeated as long as there is input pulse, right? So this is the table for the Johnson counter, right? Okay, so that's all for today's lecture, right? So today we have discussed counters, which are very important building block for different digital circuitry, right? So we can have synchronous and asynchronous counters, right? So synchronous counters are controlled by a clock, right? We can also have a counter that can count up and count down, right? So we can also design a counter that can load the data of our own desire. For example, if you want to start counting from a predefined number, then you can have the counter with the parallel load, right? And we have also demonstrated or shown that we can design or construct the counters by using T flip-flops, JK flip-flops, and D flip-flops, right? So that's all for today's lecture. So मेरी तरफ से आपको अल्लाह हाफ़िज़, अस्सलाम वालेकुम.